Calculus, video 11, two special limits. So we have two special limits that involve some trig functions, sine and cosine, that I want you to know. You should have these memorized. The first one is the limit as x approaches 0 of the sine of x divided by x. And the second is the limit as x approaches 0 of 1 minus the cosine of x divided by x. Okay. And what we're going to find out is this. I'll go ahead and give you the answer right now. The limit as x approaches 0 of sine of x over x is equal to 1. You should know that. And the second one, the limit as x approaches 0 of 1 minus cosine of x over x, this time is equal to 0. I'm going to show you the proof of the first one, and you'll just have to take my word for the second one. It's a similar proof, I just don't need to go through it twice. The proof is going to use something called the squeeze theorem, which is a lot like what it sounds. What you're looking for in the squeeze theorem is there's something you don't know. Usually a limit of something you don't know. Limit as x goes to a of something that's really hard to find, like sine of x over x. And what we're trying to do is show that the limit of the thing we don't know is somewhere between two things that we do know. The limit as x approaches a of something I know. What is something I know? I'll make it a box. And the limit as x approaches a of something else I know. It's called a triangle. And if we can show that the limit as x approaches a of the box equals, say, a number, let's call it 5. I like 5. And the limit as x approaches a of triangle also equals 5. Then we've squeezed the limit of the thing that we don't know to show that it must also equal 5. The limit as x approaches a of the thing we don't know, we know it's more than or equal to the limit as x approaches a of the box. It's less than or equal to the limit as x approaches a of the triangle. If both of those go to 5, then our limit must also go to 5. There's no other place for it to go. We're squeezing in the middle. Kind of the picture is this. The top function goes to 5. The bottom function goes to 5. So the thing that is kind of wild and crazy, even though it might be wild and crazy, has to go to 5. That's the idea of a squeeze theorem. So we're going to use that here. We're also going to show you a geometric proof. And I always find these interesting. We have these very algebraic topics here. This limit as x goes to 0 of sine of x over x looks very algebraic, but sometimes the easiest way to prove those is actually through a little bit of geometry, if you will. Okay, a couple things we need to know since we're going to use some geometry for this proof. The area of a triangle, you should know that the area of a triangle is 1/2 base times height. The second one is the area of a sector. A sector is simply a portion of a circle. Let me get a little bit of sector is a portion of the circle. All right, so if you're picturing a circle, a sector is the portion, any portion coming out from the center. Any sort of like a wedge, here. That area right here, that whole thing, is called a sector of a circle. It's a pizza slice, really. The area of the sector of a circle is 1/2 times the angle, and the angle here we're talking about is the angle, the central angle, theta. This angle theta right here, and that theta must be in radians. Theta in radians. And the radius, r. So area of a sector is 1/2 times that angle in radians times the radius squared. That's how we find the area of that particular sector. And we're going to work on a unit circle. So if you want to take notes along with this, draw a big unit circle on your paper. I very much encourage you to take notes along with the videos. It's good to write things down. It helps you remember them, and it gives you a reference to go back to. In this particular case, I'll give you the option, write it down, don't write it down, and just kind of follow along if you want to do it that route, or if you want to write it down, that's also fine. This is one I just want to show you a proof of something for a couple of reasons. One, to introduce us to some geometric proofs, but also it reminds us of some valuable things that we could use later on, like an area of a sector of circle equaling 1/2 theta r squared. I mean, honestly, if that's all you take out of this, I'll still be pretty happy. Okay, the proof goes something like this, and the first time I saw the proof, I was like, well, that was really weird, but the more you get used to it, you're like, oh, that's pretty brilliant, really. What we're going to do is we're going to squeeze the sine of x over x between two things. And so we have to create that here, and we're going to create it using three shapes. All right, the three shapes are going to come from this right here. The first thing we're going to do is we're going to have a line extending through the circle. Remember, this is the unit circle, so the radius here is 1. And creating a triangle that comes straight down like this. This is a nice right triangle here. This is the point xy. We don't know what that point xy is, but it's some point xy on the circle. And we do know that the radius of the circle is 1. So what we're going to do is we're going to get the area of that green triangle. All right? We want the area of this green triangle right here. That's going to be one of our shapes. Okay. The second shape, so let me just kind of, we have this green triangle that looks like that. The second shape we're going to use, I'll put with orange for this one, is the sector of the circle. Right there, with this particular angle theta, and the radius, radius here, the sector of the circle. We're going to find the area, right, of the sector of the circle. That's our second shape. And our third shape is a triangle, another triangle, but a smaller triangle this time, that looks like this. It's this triangle. And so, third shape, we're going to find the area of that triangle. All right, so those are our three shapes. The big triangle on the outside, the sector of the circle, which for some reason doesn't look very sector-like. Let me try that again. That's a little better, kind of snow cone looking. And then the inside triangle. Now, since I want to find something about sine of x over x, that's going to have to come from the middle area. And what I want to do is find the triangle, two triangle areas are things I should be able to calculate. All right, so a couple of things. We know we have a point xy up on the circle there. They're in green, that green dot. We have an angle theta. We have a radius r, and the radius r is 1. R equals 1 because this is the unit circle. Which means this point down here, we're calling red, must be the point 1, 0. Right, it's at the unit circle, hasn't gone up at all. This must be the point 1, 0. So let's calculate the area of each of these shapes. All right, let's start with the small triangle. The small triangle in black there, the area is equal to 1/2 base times height. The base of that triangle is 1. But what's the height? What is the height of that black triangle? Well, the height, we don't exactly know what it is, but it is given by the y value. The height goes up to the point there, xy. The height is given by the y value, so y must be the height. So the area here is 1/2 times the base, which is 1, times the height, which is y. Good. kind of good. I don't want to leave it just y. So we have a is equal to 1/2 y. I'm going to try to write these things not in terms of x's and y's, but in terms of theta, right? I want to do it in terms of theta. So we have this angle theta here. We know that for any point on any circle, the y value of a circle is r times the sine of theta. The x value is r times the cosine of theta. So this point xy here is r cosine, can't probably read that, let me try that again, is equal to r cosine of the angle, r sine of the angle. But since our r value is 1, on a unit circle, any point xy on the unit circle can be given by cosine theta for the x value, sine theta for the y value. So since our height here is y, and we're on the unit circle, the area can be, instead of 1/2 y, area equals 1/2 sine theta. All right, so we have our first area. The area of the small triangle is 1/2 sine theta. Let's go with the area of the sector of the circle there in orange. For that one, we know that area is 1/2 theta r squared. Okay, this one's not too bad. R is 1. It's a unit circle. So this area is 1/2 theta times 1 squared, or just 1/2 theta. Very good. And then the green triangle, just to give myself a little bit more room here, let me give myself some space down here. The green triangle, big green triangle, right angle here. Let's take a look at that on our picture. We know the area is 1/2 base times height. What is the base of that green triangle? Well, it's the same as the base of the black triangle, which is 1. So the area is 1/2 base height. That's 1/2 1. What's the height, though, of our green triangle? All right, so the height here, that's a little bit tougher. Thankfully, we can use a little bit of trigonometry to help us out. For any triangle, go back to just basic trigonometry. We have an angle theta. We know that the tangent of theta is the opposite side divided by the adjacent side. The tangent of theta is the opposite side divided by the adjacent side. In this case, let's call that opposite side m, just because I need a letter there. So the tangent of theta for the green triangle must be equal to the opposite side m divided by the adjacent side. But how long is the adjacent side? It is 1. Therefore, the tangent of theta is equal to m. Or said a better way, m is equal to the tangent of theta. So m, this height m, is equal to the tangent of the angle theta. That's also kind of a nice picture for a unit circle, that if you draw a triangle through one of the points and then go straight down onto the point 1, 0 there, the height there is equal to the tangent of the angle. All right, so very good. So we have tangent of theta for the height. Right, the height there is tangent theta. The base is 1, so it's 1/2 times 1 times the tangent of theta. So we have all three areas now. And we can see by the picture that the area of the black triangle is the smallest, the area of the orange sector is the middle, and the area of the green triangle is the biggest. So we have the, I'll try and keep color coding here. Area of the triangle, the black triangle, must be less than or equal to orange. Area of the sector, which must be less than or equal to the area of the big triangle. That means the area of the small triangle, 1/2 sine theta, must be less than or equal to the area of the sector, 1/2 theta, which must be less than or equal to the area of the green triangle, which is 1/2 tangent theta. All right, you're looking at this, and hopefully you're saying they all have a half in them. Why not multiply everything by 2? Sounds like a good plan. Sine theta is less than or equal to theta is less than or equal to tangent theta. All right, let's see if we can go back here and get what we wanted to. We have the sine of theta is less than or equal to theta is less than or equal to the tangent of theta. But what I wanted from the very beginning is to know something about, way up at the top, sine of x over x. And so I know I have sine of x over x here, but for right now in this proof, picture x as being theta. Right, so eventually, instead of thetas, we're going to replace those with x's. We're going to just do sine of theta over theta. Right, so when you think x in that sort of sine of x over x, think theta, sine theta over theta. My middle term is just theta, or x if you want. So what I'm going to do is I'm going to divide every term by sine theta. So I'm going to take this term divided by sine theta, this term divided by sine theta, this term divided by sine theta. Now the first one is pretty easy. Sine theta divided by sine theta is 1, is less than theta over sine theta. It is less than or equal to, on both of those, is less than or equal to tangent over sine theta. But remember, tangent is sine theta over cosine theta. So if we take tangent and divide it by sine theta, just like multiplying by 1 over sine theta, the sine thetas cancel, and I'm left with 1 over cosine theta. All right, we're getting close. We have in the middle theta over sine theta, but what I wanted was sine theta over theta. So let's flip them over. Let's reciprocate. The reciprocal of 1 is 1. The reciprocal of theta over sine theta is sine theta over theta. And the reciprocal of 1 over cosine theta is cosine theta. But remember, when you reciprocate, the inequality signs change. Right? As a reminder, 1/3 is less than 1/2. Right? 1/2 is bigger than 1/3. 1/3 is less than 1/2. But if you flip those over, 3 and 2, 3 is bigger than 2. All right, so when you reciprocate, you need to change the inequality signs. So now our inequality signs look like this. And we don't often write 1 is greater than or equal to sine theta over theta is greater than or equal to cosine theta. We use the less than symbols, so we're going to rewrite it like this. Cosine theta, that's the smallest one now, is less than or equal to the sine theta over theta is less than or equal to 1. Now we found our sine theta over theta in the middle. We're going to limit all of these to where theta goes to 0. So every one of these gets a limit as theta goes to 0. And let me scroll back up here and show you what I'm talking about and why we use these three shapes and what's happening. Picture, if you will, the angle theta here, written in orange, this central angle, going to 0. Right? If theta goes to 0, that means it's going down. It's coming down this direction. What happens to all three of the shapes as theta goes to 0? Let me just give us a picture down here. New circle. We had our theta kind of up, is about a 60-degree angle. What happens to all three shapes is I let theta get smaller. There's your big green triangle. There's your sector. And there is your inside triangle. Do you notice how all three shapes are getting closer together? They're kind of approaching the same area. Okay, very good. So we will take the limit now as theta goes to 0 of cosine theta is less than or equal to the limit as theta goes to 0 of sine theta over theta is less than or equal to the limit as theta goes to 0 of 1. Alright, well, what is the limit as theta goes to 0 of cosine theta? We can do direct substitution there. The cosine of 0 is 1. So 1 is less than the limit as theta goes to 0, sine theta over theta, is less than, as theta goes to 0 of 1, that's still just 1. So by the squeeze theorem, we see that 1 less than or equal to the limit as theta goes to 0 of sine theta over theta is less than or equal to 1, means that the limit as theta goes to 0, sine theta over theta must be equal to 1. Or if you like, the limit as x goes to 0, sine x over x equals 1. We have proven this. A nice geometric proof using the squeeze theorem. Before I leave this though, I want to point out something that we're going to use as you get into Calc 2. Something really interesting. So sine of x over x equals 1 as long as x goes to 0. Another way of saying that is, if x is pretty small, multiply both sides by x here. If x is small, if x goes to 0, if x is small, the sine of x is equal to, multiplying both sides by x. In other words, and this is kind of an important statement later on, the function y equals sine of x and the function y equals x are very similar, are almost the same for x near 0. Y equals sine of x and y equals x are almost the same for x near 0. In fact, if you were to draw y equals sine of x, and draw y equals x. Perfect there, but you can kind of see, and a better drawing would show us a little bit better, that as long as our x values are near 0, kind of in this range here, as long as our x's don't leave too far from 0, the sine of x function and the just y equals x function, that line, there's not that much difference to them. Try going out to Desmos and graphing on the same curve y equals sine of x and y equals x. And if you stay close to 0, those two curves are pretty close together. This is going to lead into Calculus 2 when we do Taylor polynomials. And one thing you'll know about the Taylor polynomial for sine of x, this is a really interesting concept, where we take these curves, right, these sine of x, these difficult functions, if you will, and we rewrite them in terms of polynomials. Sine of x is equal to x plus some other stuff. As long as x is close to 0, sine of x is basically equal to x plus a little bit of error term there. All right, that is all for my proof. Do remember, right, you should memorize both of these here. The limit as x goes to 0 of sine of x over x equals 1, and the limit as x goes to 0 of 1 minus cosine of x over x equals 0.